so today, the general linear inverse. And so, so far we've been talking about the Fourier transform and the inverse Fourier transform, which is virtually the same as the Fourier transform. And there's a lot of reasons to do this, because you have the fast Fourier transform, which is a way of very rapidly calculating this thing. And it's well understood that people have been hacking away at it for a couple hundred years. But it turns out you can rephrase the problem of what we're doing, what the scanner is doing to generate the signal, and then trying to figure out from that signal what the brain looks like. You can rephrase it as basically just a simple linear inverse. And we didn't talk about inverses, but we talked about linear operations last time, where you have a vector, and you have a matrix that's operating on a vector to generate another vector. So that's a linear transform, where you have like a matrix of numbers, and it does something to a vector. And what can it do? It can basically sort of rotate it or stretch it, one or the other, or both, or do nothing. Just leave it the same, and then it generates another vector. And so we can think of what's going on with how the scanner generates the signal, and then how to invert that. We can sort of think of that as basically just a simple linear operation, because the Fourier transform turns out to be just a linear transform. It's doing a linear operation on its input. So why would we want to do this? So one of the reasons is we talked about the distortions that you get in an image, and there's a variety of things that cause distortions, but one of the things that causes distortions is when you turn the gradients on and you try to wrap up some spin phase stripes across the brain, just stamp these little, systematic variations in phase of the precession across the brain with the gradient. You don't do a perfect job of it. And so if we write out the signal generation part of the Fourier transform, and just write it out in 1D. So for each spatial frequency of signal that we're getting back from the brain, that's equal to just the sum over all x done by the RF coil of whatever the value of the brightness of the brain image at a particular point times this stripes. And these stripes were kind of the perfect stripes. So kx times x, and then this is summed across all x. So the problem was, this is an equation that represents what the scanner is supposed to be doing to generate a Fourier transform of the brain. And the problem is this part here. This part here is a perfect set of stripes across the brain. But in reality, the stripes are not perfect. And so if they're not perfect, then the equation doesn't quite hold. And so that's what we're going to talk about. Like, how can we have a more general formulation of what's going on here that takes into consideration that the stripes are not perfect. And not just that the stripes aren't perfect, the coils don't pick up uniformly from the entire head. The coil phase isn't quite right. There's a whole bunch of things that are imperfect, that we're assuming are perfect when we use this as a model of what the scanner is doing. And so we can call this is the equation that describes what the signal is, but if you think of this in terms of something like, EEG and MEG, you can sort of think of this one as the forward solution, because what it's doing is it's mapping the brain to the data that we pick up. And then what we want to do is we want the inverse solution. And the inverse solution is we've got this data, and now we're going to try to figure out like what the brain is. And so in the case of the Fourier transform, the inverse solution is very straightforward. It's just for a point in x, we just do exactly the same thing again. And so what is that? Let me just put this one down slightly lower because I'm going to need a little more space on that side. So if we just look at how the inverse solution works, we just sum across all spatial frequencies, but now we're taking that signal that we got over here, and I put a vector on it just because it's a complex valued signal, and we do exactly the same thing except there's just a plus. And so that's the beauty of the Fourier transform, because everything is exactly the same, and then we're summing across all spatial frequencies. And so all we've done is we just take this thing and stick it in here and then do the same thing to it again. And it's all good, we get an image. So why is this a linear transformation? So if you look at this, you can see, and then this, we can think of this as the inverse solution. That would be like something like an MEG, where you've got a signal and you recorded the signal that came out of the head, and you're trying to sort of figure out like where it came from. So what's going on here? So we mentioned it was kind of like a dot product, because you're multiplying this a whole bunch of things times each other and summing them up. But if you look at this thing here is a smaller thing than this thing in some sense, because this one just has an image value at each point, at each x point. But you see this has two variables in it. So it's got, spatial frequency and then also image point. And so this thing is actually a matrix. So you can think of this thing as a matrix. This thing, you can think of it in a finite case as a vector. It's just a vector of values of the brightness at each image point. But this thing is actually is a square of numbers, because you need a value for this thing at each x point, but also at each spatial frequency point. So if you look at it that way, then what we can do is we can just rewrite this thing out as just a linear transformation, because that's actually what it is. And so I'm using this same s here, but that's a small s for essentially the vector of complex numbers. So this thing, because this says, for each spatial frequency, we have a complex number. And so what I've done here is I've just said, okay, so here's a vector, and that vector just consists of a whole string of complex numbers. The vector that I had up here was my sort of non-standard way of saying it's a complex valued thing that has real and imaginary. In this case, I'm not doing that. I'm just saying this is just a string of numbers. They happen to be complex. So basically we can sort of, economically write this out as that string of complex numbers is just equal to a matrix operating on another string of numbers. And the other string of numbers is the image values at each point. So this thing is basically a vector. So this guy is a vector, a 1D vector, and this guy is a vector. But this thing is actually a matrix of numbers, because you have one of these things for each x, every combination of x and y. So basically you just have a string of complex numbers which equals a matrix operating on another string of complex numbers. These are the image numbers, and so they happen to have 0 for the imaginary part, but they're just a string of complex numbers again. Now, when you look at this, you might wonder, like, what about 2D or 3D? Like, this just looks like a string of numbers, like a line of numbers, but you can easily sort of incorporate 2D into this. So here's a 2D image. So how can we turn that image into a vector? Well, we can just like string out all the lines into one long vector. So you can just do that. Just take all the lines. Take this line out and put it here, and then take the next line out and put it here. And so then we still have just a one-dimensional vector. And then we're operating on that with this matrix. And the matrix could get a little more complicated if we have effectively a two-dimensional vector, but this way of sort of embedding the two dimensions into a vector into just a one-dimensional vector is very common. So if we write out the matrix, what does it look like? So it looks like we've got this set of signal values that are coming out for each x point or each xy point, and then it's multiplied by a square matrix. And so here's the square matrix. And what are the dimensions of this matrix? So the dimensions, so x is going in that direction, and then kx is going in this direction. So that there's a table of all the possible combinations of x and kx. And then it's operating on that image vector. So here's the image vector, and that one has x going in this direction, or xy if we're doing this, and this one has kx going in this direction. So basically, this is just a simple way of just writing out effectively the same thing. So we're just multiplying. We're just doing a matrix multiply. The only difference from a regular matrix multiply is that all the entries in here are complex. So at each point here, each guy here is going to have like a real and an imaginary, and same way here. So at some point in this matrix, this guy is going to have a real and imaginary at that point. So why would we want to do this? Well, now we can stick any old thing in there, any old imperfect stripe. And so what we want to do now is just write out an equation that we would use in order to insert all these entries in here. And so I haven't really talked about echoplanar imaging like you do for functional MRI. I'll talk about that next week. But I'll give an example from it, so I'm slightly jumping ahead. But so if we do that, so here's our f that we're going to stick in there. So this is a complex value. And so for a given xy point in our matrix, plus a given xy point in the brain, and a particular time. And so why is time in there? Well, we're collecting the data over time, and so things are happening like T2 decay is happening. And so that means that the actual amplitude, the effective amplitude of a spin stripe, if we wait around for a while, is going to be less because it's been decayed, and so the signal coming out of that little spot of the brain is going to be, if we record the data point a little bit later, is not going to be as strong as it would have been, and that will effectively sort of make imperfect stripes that won't be captured by this perfect Fourier transform. So what are the kinds of things that we could add in that would sort of characterize what the imperfect stripes were doing? So the very first thing is we could put in the gain of the coil. So if you have a coil somewhere like this, and there's a RF coil coming here, recording from this part of the brain, that depending on where you are in the brain, XY in the brain, the signal is going to be vary quite a bit. I mean, it might be like 1/10 as big by the time you get to the front of the brain, and so that's not included here, and so we could just include that. So as a factor, so just put how strong the signal that you would expect. Now, you may immediately be thinking like, well, where are you going to get that number from? And that's a very good question. So one of the problems with this general approach is that, and it's kind of like when I was younger in inverse, I really can't spell inverse there. Inverse, there we go. Still not right. So when I was younger, I thought this is totally the way that you should do it, because we know that it's not perfect, and so why don't we just do the real thing? But the problem is we've got to get these numbers from someplace. And so where do they come from? Well, how could we get this number? So this number, what we could do is we could record from the body coil, which is the one that we normally use to transmit to the entire body. And instead of just transmitting with it, we could record from it. And the body coil is far distance away, and so it will have the same brightness for all the different parts of the brain. And then we could record from this coil, and then we could sort of compare the two and figure out like what this number is. So, and that would take another scan. Might not be a long scan, maybe just a couple seconds, 5 seconds might be enough to do it. But we would have to get that information from another scan. So that's one little thing we could add. Now, another thing, so this guy is a real number, coil gain. So this is, one entry in F matrix. So that guy's a real number. It just says, how bright are you going to expect a brain point to be to contribute to the signal in this coil, and then that will sort of multiply complex numbers down the road. It will change their length. But the other thing is that the phase of the oscillation that the coil picks up is not the same. It's actually dependent on where you are in the brain, and so you've got another number in here, which is whatever that phase offset is. And what does that mean? That means like, if you've got an oscillating proton over here versus an oscillating proton over here, the signal that the coil picks up is slightly different. Not slightly different, it could be quite different, like 25 or 25% different, something like that. And so So that depends, that phase error depends on where you are in the brain. And so that whole thing is some additional, phase angle. So this is, a phase angle. So this guy is complex. So this whole thing is, complex. And so you remember what it's doing to whatever's over here is just adding to the angle, So when you multiply, complex, equals add angle. So when you multiply by this complex, you're just incrementing the angle. So this one is just changing the length of the complex number, but this is amplitude 1. You're multiplying by an amplitude 1 thing that just rotates, just rotates the vector. And then we've got some T2 decay in there. And the T2 decay, so this example I was giving was for, for EPI. And what EPI is when you're recording K-space, you basically go back and forth across K-space like this and record all of K-space in one shot. So, one shot. What does shot mean? So shot just means like one, RF. One RF 90-degree pulse. So now we've got some T2 decay occurring, and why do we need that? Well, if we're spending 50 or 60 milliseconds doing this, that's a lot. There's a lot of T2 decay occurring. So by the time we get to the top of K-space, the signal is going to be a lot smaller. And so not only that, it's going to vary with time, but we're going back and forth through K-space, and so that means like the time will be reversed, relative to Kx, because we're going back and forth. So we got to stick all that in. So how do we do that? So this is just a decay. So if we just have, e to the minus something, then you think of start at 1, think of that. Whereas as this thing, this thing, you think of, oh, I'm on a amplitude 1 with a particular phase angle. But this e to the minus with no I in there just means like, decay. And then we'll have like, a whole bunch of messy things in here because we're going back and forth across K-space. And that's the bandwidth in there, plus, whatever the echo time that we started at, that whole mess divided by T2. So what are all those things in there? So this would be, this guy's the bandwidth, or 1 over the bandwidth. That's how much time it takes between each sample. And it could be plus or minus because maybe we're going back and forth across there. And this one, this one is the KY. This one is, time for one line of K-space. This guy is, sort of the KX. And that's how much time there is between each successive sample. And this is like, the TE when we first start down here, starting TE, start TE. And then there's this. What's that? Well, now we've got to know the T2 even before we started. See, now you start to see what the problem is with doing it the right way. It's just, where are we going to get that information from? So you could try to do another quick scan to try to estimate what the T2 was, or you could just say, well, the T2 of the gray and white matter is about the same, and we know approximately what it is, and we'll just stick a number in there. So this thing is just, this thing is just a decay term T2 decay. And this is just a real number, so that's, it'll be a real number slightly less than 1 that we'll sort of multiply the complex numbers by. And then, but what about a B0 problem? So what if the field isn't completely flat, so the precession frequency is different in different parts of the head? We know that occurs. That's a source of distortion in the images. And how does it cause a distortion? It messes up the stripes. It causes them to be bent, sort of like curvy bent. And then we assume we've got perfect stripes when we do the inverse Fourier transform, and then that results in a spatial distortion. So that's another E. So this guy is one of these e to the minus I businesses, because it's going to change the expected phase of this part of the stripe by multiplying by a complex number, also known as adding the angle of whatever is past the I in this e to the minus I. And so what is that one? So that one's going to be, well, there's the gyromagnetic ratio times whatever the B0 delta B0 offset is, and that's going to be a function of like where you are in the brain, because different parts of the brain have different B0 offsets. And it will also be a function of this mess here, because you have to consider how long the B0 offset had to mess up the phase. And so since you're recording the data at different points in time, the ones that are up toward the top here are going to have a bigger phase error, because that fixed B0 offset, this guy, has had a longer time for to mess up the phase. And so we need that whole thing in there again. Depending on plus TE, okay. That's good. So that's yet another, so this guy is this guy's a complex amplitude 1 number that fixes up the B0. But now the problem is, where does this come from? So this is, local B0 offset. Is there any way of actually sort of measuring that? Because it's XY dependent, and there is. So we could do another scan. And that other scan would basically try to estimate what the B0 offset is. And there's something called a field map scan. And what you do is you just do a scan with 2 echoes, and then you sort of compare the 2 echoes to each other. Because those echoes occurred at different times, then you can sort of try to estimate how bad the phase offset has been. So look at the phase of those 2 echoes and just see, did this one get further ahead than this one? If so, that means there's the worst B0 offset. And so there's a way to do that. You could do another scan. It's not, maybe this one takes a little longer, maybe 30 seconds or something like that. And then we could try to, estimate. So a complex, B0 offset. And what is that doing? Well, it's just messing up the stripes. And so we're just trying to sort of fix up the stripes. And then last but not least, we got the stripes. And so here's our perfect stripes. So this would be e to the minus I 2 pi, and times all this other stuff, delta kx times x. So that's these guys, plus, but all sort of factored in because we're going back and forth, plus n times delta ky times y. And then this whole thing sort of multiplied by our image increments. So these are the perfect stripes. So perfect stripes as modified by maybe the B0 is off, and then as modified by, well, it's in different parts of the image, it's decayed different amounts, and different parts of the image, maybe the phase is off because the coil phase wasn't quite correct, and then also multiplied, scaled by what the coil gain is. And so now we have one number. So this guy is, one number, and so this guy goes over here and in there. So then all we got to do is just fill out all the rest of the numbers. Now, the good part of it is that we only have to do this once, assuming that the head hasn't moved around in the scanner too much. And so then we could just make this thing once, and we could use this for all the different images that we're acquiring. Okay, so that was the forward solution, so that we turned this thing, which is nice and really simple, into this gigantic mess, but that's okay. So now we have to solve this equation here, and so what does that mean? So now we've got to somehow invert this equation. So this says, signal equals matrix, times vector, but we want to solve for the I. So we want, I equals some inverse matrix operating on the signal vector. That's the solution. And so how do we do that? So any questions so far? So like I said, like when I was younger, I said this is definitely the way to go, because now you'll actually just sort of figure everything out. But the problem is you got to collect these extra scans to sort of figure out the B0 offset. You got to estimate the T2. You got to estimate this sort of coil phase problem and coil gain problem. And one thing to keep in mind is that if somehow the scan that estimates the B0 offset is screwed up, like for instance the person coughed during the scan, one problem with this approach is that that's going to be used to reconstruct all the images. And so if you screwed up this sort of test scan, that potentially could screw up all the rest of your images. And so then you probably need another scan in there just to check was this scan screwed up? Did the person move during the scan? So we need some additional measurements to make sure that the person, or maybe do this one twice and see if they're more or less the same. So you can see it before long. It sort of you come back to this. You go let's just hack that one. That's easier. We'll just do a little quick and dirty hacks on this one instead of sort of dealing with the sort of messy reality. Okay, but we still haven't inverted. So let's just let's sort of show how you would solve this. Linear equation or linear system of equations. It's basically you're basically solving a system of equations when you solve for I in something like this. And so the way we do that is you have to first consider the fact that we don't have a square matrix. And so why is that? It's actually a good thing. So if we write out this, so let's just start off with, so this guy is, this guy here is this. And so what's the equivalent of our, what's the equivalent of our inverse? Our inverse is, we just have to, figure out here's our image vector, and it's just once we've inverted that matrix, then we can just multiply by our inverse. So we could write it -1 for inverse, but a lot of times we'll write it plus, which means a pseudo-inverse in case we've got rectangular matrices, which we haven't explained why we have those, but we will in a second. So so this guy's a matrix, and this guy means pseudo-inverse. which means like for rectangular matrices. But it's still just a matrix of square. It's a number. It's a rectangle of numbers, and they're complex values. But it's still just a matrix doing matrix multiply times our signal vector. So basically, that's just this guy right here. So we just take our signal vector and stick it in here. And then all we need to do is just multiply it by a matrix, and we're done. So now the problem is, how do we get that matrix, that inverse matrix? And why is it rectangular? So it's rectangular in a good way. So the good way is that we've got multiple coils. And so let's just write out this first equation like this one, with multiple coils. So now we've got a longer, we'll just write it out for 2 coils. So basically what we do is we have our first coil, so here's the S vector, and so here's coil 1, coil number 1, and we got another set of numbers that came out of coil number 2. So, and in real life we've got 32 coils or 64 coils, and so then there's going to be like a really long vector here. But that's a good thing, because we're solving for just one set of numbers, which is the image values, and so that's a good thing because we've got more data than we need. So there's 2 ways that the matrix could be rectangular. It could be rectangular in the form that it's underdetermined. We're solving for more numbers than we actually have data, or it could be overdetermined, and that's what we have here. So we're solving for less numbers than we have data. So this S vector is going to have more number of data points than there are image data points. So here's our S vector. So, and it's a 2-dimensional image, so this would be like kx, ky, going down like that, and then another copy of kx and ky coming out of the other coil, going down there. And then we're multiplying this rectangular F matrix. And so the F matrix is going to be divided up like that too. So there'll be, so here's our forward solution F matrix, and then we'll have a coil 1 version of it, and a coil so there'll be a whole set of numbers for coil 1, but they'll be different for coil 2 because the gain on coil 2 is different. So, but the good part of it is that the actual thing we're multiplying by is basically like that, is the same as the width of the matrix. So this is xy going in this direction, and xy going in this direction, so that should be the same because we're multiplying all the numbers here times the numbers here. And so this guy is our final image that we're trying to solve for. Okay, so xy going in this direction, and kx, ky going in this direction, and again for the next coil. Okay, so that's a good thing because that means that we've got more information than we're solving for. And so how do we figure out this inverse matrix? So we figure out the inverse matrix by like a standard equation that you heavily use if you're doing any kind of least squares analysis, exactly the same equation. So it's called the Moore-Penrose pseudo inverse. And it looks like that's the plus. So F plus, meaning like inverse, but it's kind of like a slightly messed up inverse, so it's a plus. Sometimes they use different symbols for it, typically. So what is it equal to? It's just equal to the transpose. Sometimes you can just use a apostrophe for that, but we'll put a T there. It's the transpose of these two matrices multiplied by each other times the transpose again. So now it's just like a forest of numbers. So you got two rectangular matrices multiplied by each other. And what that does is it makes another matrix that is square in the bigger of the rectangular dimensions. So, and so it, depending on what the order is. And so it turns out this is also equal to so there's two different forms of this that are mathematically equivalent, even though they involve like a large difference in the total number of numbers. So here we're multiplying this original F, so this F right here, not the F plus, but this F transpose and F are just this original matrix. And transpose just means like flip it around the diagonal. So these two things amazingly are equivalent, but they're very different in terms of how hard they are to calculate. So it turns out that this bottom one, when you multiply this rectangular matrix times a transpose, which would be a rectangular matrix that sticks out this way, what happens is you end up with a square matrix that's square in the large axis of the rectangular matrix. When you do this one, so you transpose this guy first into one that looks like this, that's long in the horizontal axis, and multiply one that's long in the vertical axis, you end up with a matrix that's just square in the short axis. And so this one turns out to be much better. So I'll just write that out. So this first one says, take a matrix that's rectangular this way. That's this matrix transposed, and multiply it by the non-transpose matrix, and then take that whole thing and multiply that by the transpose matrix again. And so when you do this, you get something that looks like that. And when you do it the other way, so this one was that first form of it. When you do it the other way, bad things happen. And so now, in this case, we start off with the transposed matrix like that, and then when we multiply that by our original matrix, which is long that way, times the transposed matrix, then we get a big square, a huge square matrix. So this one sort of like turns into a monster like that. And I left out one key symbol here, which was the -1. Okay, so -1. So that guy is a matrix inverse, and we can only do that for, we can only calculate that matrix inverse for a square one. Yeah, so key symbol I left out there. Okay, so here we're calculating that matrix inverse for this small one. Over here, we're calculating this for this really big one. So the size of the matrix will be, or kind of like the number of operations that we need to do is like, x times y squared, or that's the number of, number of entries in that matrix. In this case, it's going to be, x times y times coils squared. So in this case, it's going to be 32 squared bigger. So thousands of times worse to do this one than to do this one. So we would do this one. It's kind of strange. It's always strange to me, like, how could these be the same? And one involves like 32,000 times more multiplications than the other one. I don't know. It's kind of weird, but it's just the way it is. So this this would be the way that we would calculate this guy. So it's the whole purpose of calculating this guy. And then once we've got that one, that guy, goes up over here. And we only have to do that once. And then how do we make our images? We just, get all our data, a whole bunch of data. Every volume comes in every second. And then we just multiply it by this matrix. This operation is very simple to do once you've done the inverse. And then we get our image. So it's just a linear operation, which you can think of as like you start up with a vector. You take a matrix and operate on it, and that just sort of rotates and scales the vector, and then you get another vector. And that vector happens to be your image in this case. So this is the most general way of trying to build in all of the actual imperfections. And have people done this? Nah, not really. So what have they done? They've done, there's a version called Sense on the scanner, which is kind of like a little bit of a, special, it's not quite, it's not this general, but it's like a special purpose linear inverse. There's another thing that we'll talk about a lot called grappa, which is, it's not really a linear inverse, but you can sort of think of it as doing kind of the same thing. In this case, we're leaving out data. And trying to sort of fill in data to sort of using a little tricky method of filling in the data. But there's another thing called, if you want to read about it, it's called compressed sense. And so one of the things that you can see here is that you've got a whole crap load of data here. And so you got way more data than the image vector that you're solving for. And because of that, it's pretty straightforward. You can say like, well, what we could do is just leave out some of the data here, because we only need like the same number of data points as unknowns. And so we could, in theory, we should be able to get by with 1/32 the total amount of data here. And so we could just leave out some of the k-space points. And so there's a lot of work on trying to figure out what data points should we leave out. And so why is it called compressed sense? Because think of like JPEG when you compress a video image, or just compress a picture. What do? You leave out a lot of the data, and we're talking a lot of the data. Like a JPEG will only be like 1/10 or 1/20 the size of the actual image that lists all the pixels, the brightness of the pixels in the image. And so it's leaving out a ton of data. It's leaving out like 98% of the data, and yet you get something that still looks pretty good. And how do you do that? Well, you do a tricky way of leaving out the data that your eye can't see easily. And so compressed sense is trying to do the same thing. Like we're way over determined, so we got a lot of extra data coming in from these multiple coils. And so what's the most optimal way of sort of compressing our image by leaving out some of the data that we're collecting, so that when we reconstruct our image, it still looks pretty good for our purposes. And so you can sort of experimentally say, like, what if we just randomly leave out data points? That's actually not too bad. But there's even better than random methods of omitting data points that will basically allow you to still end up with an image that looks really good. And this could, conceivably give you like a really, really large increase in speed, like a 10 times increase in speed or a 20 times increase in speed, similar to what you get like from JPEG compression. So if you're interested in trying to, and this is finally starting to come into the scanner, there's a few pulse sequences even from the manufacturers that are starting to do this. And so this is like a active area of interest. It's been an active area of interest for a long time, but nothing really kind of hit the big time yet, but probably will in another 5 or 10 years. So, okay, any last questions before I go over? So what we did was this is our standard Fourier transform that the magnet does, inverse Fourier transform that the reconstruction does. We can view this thing as basically just a simple matrix multiplication. A signal vector equals matrix of Fourier coefficients operating on the image vector. And then how do we do the inverse Fourier transform? We just basically find the pseudo-inverse. How do we find the pseudo-inverse? It's just basically this. And what is this? This takes our rectangular matrix here, because we've got multiple coils, builds it up into either kind of a small square matrix or a gigantic matrix. And so we don't want this one. Don't do that one. And do this one instead. And then it inverts that. There's ways to invert matrices. Inverts this square matrix. And then we get all the numbers here. And then we just do our reconstruction by just matrix multiplying our inverse times the signal vector for each new acquisition. And if we're doing fMRI, so we get another volume every second, well then this matrix multiplication is very cheap, compared to doing something like an inverse. So people haven't done this yet, but this is how you could do it. Computers have gotten faster and faster. So any final questions about sort of general linear inverse approach? It's kind of of course you could just do a plain old Fourier transform using this method, but it would be way less efficient than using the fast Fourier transform that is worked out for, right here. So this thing is much quicker to compute than trying to compute this thing down here. And then it also sort of gives you a feel for like how these things actually, relate to each other. This looks completely different. This looks completely different than this. This one's good. It has less letters in it. Okay, any other questions? Looking all good. Okay, Stan. Well, I think we'll end the recording there. Okay, better this year, a little unscrunched from last year.